There's a particular kind of beauty in the universe that can stop you cold. The kind that makes you forget what you were doing, makes you set down your coffee, makes you stare at the screen for a full minute before you realize you haven't blinked. The first time you saw a real photograph of the pillars of creation, or the Eagle Nebula, or Saturn lit from behind by the sun, something shifted in your chest. You didn't have words for it. You probably still don't. That feeling has a name in physics, though physicists rarely use it. They call it cosmic awe. The recognition that the universe, indifferent and ancient and impossibly vast, has been quietly making things of unspeakable beauty for billions of years, with no audience, no purpose, no one to applaud. Just because that's what matter and energy do when given enough time and space. They organize themselves into wonders. The universe is 13.8 billion years old. Most of that time passed before any eye existed to see what was happening. Stars were born and died. Galaxies formed and merged. Nebulae bloomed in the dark, glowed for millions of years, and faded. Black holes consumed entire star systems. Supernovae lit up regions of space brighter than entire galaxies for brief weeks before going dark again. Then, about 4 billion years ago, on a small planet around an ordinary star in the suburbs of an ordinary galaxy, the first life appeared. It was simple at first. Single cells, molecules organizing themselves into self-replicating structures. Life persisted for billions of years before any organism developed the kind of nervous system that could produce something we'd call awareness. Then, just a few 100,000 years ago, our particular branch of life developed minds capable of looking up at the night sky and asking what it was. We are very recent. Tonight, we're going to walk through some of those wonders, the most beautiful things in the universe as far as we can currently see them. The objects, the events, the structures that even hardened astronomers who've been looking at space photographs their entire careers sometimes pause and stare at. The places where the math becomes art, where physics produces patterns that no human artist could have dreamed up. This isn't a list of facts. It's a slow walk through visions. We'll start close to home, with phenomena you might be able to see with your own eyes, and we'll travel outward, through the solar system, past the nearest stars, into the deep reaches of our galaxy, and eventually out to objects so distant that the light we see left them billions of years before there was anyone on Earth to look up. Lie back, get comfortable. The universe has been busy, and tonight we get to admire its work. Before we dive in, if you find this kind of slow exploration calming, a like or subscribe really helps the channel grow. It's a small thing for you, but it matters a lot for me. Now, let's begin where beauty is closest, the aurora. If you've never seen the aurora in person, you've at least seen photographs. Curtains of green and pink and purple light hanging in the sky like cosmic fabric, rippling and swaying as if blown by a wind nobody can feel. The aurora is what happens when our sun reaches across 93 million miles of empty space and touches Earth's atmosphere with charged particles. It's a meeting between two cosmic objects, a star and a planet, and the conversation between them is light. The technical explanation is simple. The sun produces a constant stream of charged particles called the solar wind. Most of those particles are deflected by Earth's magnetic field, which acts like an invisible shield. But the field isn't a perfect dome. Near the poles, the field lines curve down toward the surface, and some of those particles slip through, accelerating along the field lines until they slam into atoms in the upper atmosphere. The collisions energize those atoms, and when they relax back to their normal state, they emit photons. Different gases produce different colors. Oxygen at high altitudes glows red. Oxygen lower down glows green. Nitrogen produces blue and pink. The aurora is the visible signature of countless atomic collisions, each one a tiny act of light, all of them together painting the sky. The colors you see depend on altitude. Below about 100 kilometers, oxygen glows green, the most common aurora color. Between 100 and 300 kilometers, oxygen glows red, which is rarer and harder to see. Nitrogen, more abundant in the lower atmosphere, contributes the blues and purples and pinks at the bottoms of the curtains. The combination produces the layered, gradient appearance that makes auroras feel three-dimensional, even though they're essentially two-dimensional sheets of glowing gas in the upper atmosphere. Solar activity varies on roughly an 11-year cycle. During solar maximum, when the sun is producing more flares and coronal mass ejections, auroras are brighter, more frequent, and visible at lower latitudes than usual. During solar minimum, the lights are dimmer and stay closer to the poles. We're currently in a relatively active phase of the solar cycle, which means auroras have been more visible than usual in recent years, with displays reaching as far south as Texas and the Mediterranean during the strongest events. But that's just the mechanism. The experience is something else. To stand under an active aurora is to feel small in a way that no other natural phenomenon quite delivers. The light moves. It pulses. It breathes. There's a famous old description from people who saw the lights long before anyone understood them, that they sing. There are sounds reported by witnesses, faint crackling and hissing noises that scientists are still arguing about. Some recent research suggests the sounds might be real, produced by electrical discharges close to the ground when the aurora is intense. Whether or not they sing, the auroras feel alive in a way that lights in the sky shouldn't. They feel like they know you're watching. In ancient cultures, the aurora was understood as something far stranger than charged particles. The Vikings believed the lights were the spears and armor of the Valkyries, riding above the battlefield. The Sami people of northern Scandinavia warned children not to whistle at the lights, because the lights might come down and take them away. Some Inuit traditions held that the lights were the spirits of the dead playing a game of football with a walrus skull. Across cultures and across centuries, the aurora has been treated as a portal, a sign, a presence. Even now, knowing the physics, the experience of watching them feels less like observing a natural phenomenon and more like being witnessed by something. The northern lights, the aurora borealis, are visible across the high latitudes of the northern hemisphere. Norway, Iceland, Alaska, northern Canada, Finland, Sweden, sometimes as far south as Scotland or Michigan during particularly strong solar events. The southern lights, the aurora australis, do the same thing in the southern hemisphere. They're identical in physics but rarely seen by as many people because there's less land near the South Pole. There are auroras on other planets too. Jupiter has them, brighter than Earth's. Saturn has them. Even Mars has weak auroras, despite lacking a strong magnetic field because the solar wind interacts with patches of magnetized rock in its crust. Anywhere a planet has an atmosphere and a magnetic interaction with its star, you can get auroras. The phenomenon is universal in a sense. Our sky's most beautiful trick is repeated across the solar system. Imagine standing on Jupiter's moon Ganymede, the only moon with its own magnetic field, and watching auroras dance over Jupiter's clouds. Imagine, on some distant exoplanet, an alien aurora in colors we don't have names for, lighting up an alien sky. Beauty isn't unique to Earth. It's just that, for now, Earth is the only place we know is watching. Let's stay in our cosmic backyard for a moment longer. Saturn, the most photogenic planet in the solar system. The one even people who don't care about space recognize instantly: the rings. Saturn has the most spectacular ring system in our solar system, and possibly the most beautiful single object in the planetary realm. Photographs taken by the Cassini spacecraft, which orbited Saturn from 2004 to 2017, are still circulating online as wallpapers, screensavers, posters in classrooms. There's a particular Cassini image taken when Saturn passed in front of the Sun and the light scattered through the rings, that shows the entire ring system glowing from behind, with Saturn itself appearing as a dark silhouette. In that image, looking carefully, you can see a small pale dot suspended in the rings. A label points to it. That dot is Earth. Earth, photographed from beyond Saturn, with the rings of a gas giant in the foreground. The most distant photograph of our planet ever taken from a place we'd been to with a working spacecraft. A reminder of how small we are and how strange the universe is. The rings themselves are made of mostly water ice, ranging in size from tiny grains the size of dust to chunks the size of houses. They're surprisingly thin. Despite being hundreds of thousands of kilometers across, the rings are only a few tens of meters thick in most places. If you scaled Saturn's ring system to the size of a soccer field, the rings would be thinner than a sheet of paper. The rings are organized into distinct bands, each labeled with a letter by astronomers in the order they were discovered. The A ring, the B ring, the C ring, and so on, out to the faint G ring and the diffuse E ring far from the planet. Between the A and B rings is the Cassini division, a relatively empty gap created by gravitational interactions with Saturn's moon Mimas. Particles that try to settle in the Cassini division get pulled out by orbital resonances, leaving the gap mostly clear. Other gaps in the rings are caused by tiny moonlets embedded in the ring system itself, sweeping out clear paths as they orbit. The structure of the rings up close is extraordinary. Cassini photographed details that nobody had ever seen, including bright streaks called spokes that appear and disappear in the B ring on timescales of hours. The spokes are thought to be tiny dust particles temporarily lifted out of the ring plane by electrostatic forces. They look like radial smears across the rings, like spokes on a wagon wheel, hence the name. Voyager first noticed them in 1980, and astronomers spent decades trying to understand what they were. Cassini gave us the close-up data needed to confirm the electrostatic explanation. How did they form? We're still not sure. One theory is that they're the remains of a moon that wandered too close to Saturn and got torn apart by tidal forces about 100 million years ago. Another theory says they could be much older, possibly as old as the solar system itself, 4.5 billion years. The question has been actively debated. Cassini-era research pointed toward the younger estimate, looking at the freshness of the ice and the rate at which dust contaminates the rings. More recent studies have reopened the case for ancient rings, suggesting that dust contamination may not be a reliable age indicator. The honest answer is that we don't yet know whether the rings are 100 million years old or a few billion. Either way, we're alive at a time when they're still spectacular. This means the rings might also be temporary. Saturn's gravity is slowly pulling material from the rings into its atmosphere. NASA estimates that the rings are losing tons of material every second, raining down onto the planet as a kind of slow ice rain. In about 100 million years, give or take, the rings might be gone entirely. We're alive during the era of Saturn's rings. Astronomers in the deep future will look at Saturn and see a boring, banded gas giant like Jupiter with no rings to speak of. They'll have to read about the rings in old textbooks. The Cassini mission ended in 2017 with one of the most poetic acts in space exploration. After running out of fuel, NASA deliberately plunged the spacecraft into Saturn's atmosphere, where it burned up like a meteor. They could have just left it in orbit, but they were worried that an uncontrolled spacecraft might eventually crash into one of Saturn's moons, particularly Enceladus or Titan, which might harbor microbial life. Better to destroy Cassini in a controlled atmospheric entry than risk contaminating a potentially habitable world with Earth bacteria. So Cassini, after 13 years of orbiting Saturn, sending back hundreds of thousands of images, plunged into the planet and burned up. Its last transmission was beamed back to Earth in real time. Telemetry data that arrived 83 minutes after the spacecraft was already gone. We received the final messages from a probe that, by the time we read them, had already ceased to exist. A ghost speaking from the other side. Beauty is not eternal in the universe. Even the most photogenic planet in our solar system is shedding its most beautiful feature slowly before our eyes. We get to see it. The future doesn't. Now, let's leave the solar system. We're going to travel many light years to look at our first nebula, the pillars of creation. You've seen them. Even if you've never read a science book, you've seen this image. It's been on textbook covers, NASA posters, magazines, museum walls, t-shirts, mugs. It might be the single most reproduced astronomical image in human history. The pillars of creation are part of the Eagle Nebula, a star-forming region about 6,500 light-years from Earth in the constellation Serpens. The Hubble Space Telescope took the most famous photograph of them in 1995, and the image immediately became a phenomenon. 3 towering columns of dense gas and dust, illuminated from behind and within by the light of newborn stars, rising thousands of times higher than our entire solar system. They look almost biological, like fingers, like trees, like cathedrals. The names people use for them are always reaching for organic comparisons, because the shapes don't look like dead matter. They look like something growing. The longest of the 3 pillars stretches roughly 4 light-years from base to tip. Light, traveling at 300,000 kilometers per second, takes 4 years to traverse a single one of those columns. If you tried to travel to the top of one of the pillars from the bottom, even at the absolute physical speed limit of the universe, you'd need 4 years for a one-way trip. The pillars are taller than the distance from our Sun to the nearest other star. They're some of the largest individual structures we routinely call objects in astronomy. What you're actually seeing is a nursery. The pillars are dense regions where new stars are being born, right now, inside them. The gas and dust are slowly collapsing under their own gravity, forming protostars at the cores of small clumps within the columns. Some of those protostars will eventually become full stars. Some will not. Some are already heating up enough to push the surrounding material away, slowly evaporating the very pillars that gave them birth. The pillars are temporary. They're being destroyed by the radiation from the newborn stars they made. Inside the densest knots, called evaporating gaseous globules or EGGs, individual stars are forming in cocoons of gas and dust. Some of those eggs have been observed directly. Astronomers can see them as small dark blobs against the bright background of the pillar's interior. Each blob will eventually become a star, possibly with planets, possibly with life. Each blob is a tiny stellar genesis happening right now, frozen in its earliest moments by the limit of how fast we can observe. When the James Webb Space Telescope photographed the pillars in 2022, it gave us a new view, in infrared this time, that lets us see deeper into the dust. The new photograph reveals stars and structures that Hubble couldn't see, hidden inside the columns. The pillars become more transparent, more revealed. You can see individual newborn stars glowing faintly inside them, like candles inside lanterns. The Webb image also reveals something Hubble couldn't show: jets of gas being ejected from young stars, plowing through the surrounding nebula at hundreds of kilometers per second. These jets are signs of stellar youth. Newborn stars often expel matter from their poles as they form, creating shock waves that compress nearby gas and trigger the formation of more stars. The pillars are not just a passive nursery, they're a self-perpetuating one. The first stars to form trigger the formation of the next generation, which triggers the next. Here's a strange wrinkle. Some astronomers have proposed that the pillars may have already been destroyed. Spitzer telescope observations from 2007 detected a hot dust cloud near the Eagle Nebula that some researchers interpreted as evidence of a recent supernova, possibly close enough to have blown the pillars apart. The idea is that because the pillars are 6,500 light-years away, we wouldn't see the destruction for another 1,000 years or so. The hypothesis is debated. More recent JWST images still show the pillars intact-looking, and not all astronomers accept the supernova interpretation. But the possibility lingers. The image we have, the famous photograph, might be a record of an object whose end is already in motion. It's a strange thing to sit with. We are looking at light that left the pillars 6,500 years ago. They might be exactly as they appear, still standing, still birthing stars. Or they might already be gone, with the news of their destruction still en route to us. Either way, the photograph is a window into a past we cannot directly verify. This is what cosmic photography is. Images of the past, sometimes a past so distant that the subject may no longer exist. The light is real. The thing the light came from is, in some cases, only probably still there. But the photograph is real. The pillars were real when they made it. They stood in space for thousands or millions of years, slowly making stars, slowly being destroyed, beautiful and brief. The fact that we got to see them, even from far enough away that we were seeing them already centuries old, is a kind of cosmic luck. The universe is full of things that come and go. A few of them, by accident, line up with our gaze in the right way at the right time. We catch the light. We make the photograph. The thing itself fades from existence, but the image lasts. Beauty in the universe is fragile. We get glimpses, not permanence. Speaking of nebulae, let me show you a few more. The Cat's Eye Nebula is one of the most complex and gorgeous planetary nebulae we've ever observed. It sits about 3,000 light-years from Earth in the constellation Draco. The name Planetary Nebula is misleading because it has nothing to do with planets. It refers to objects that early astronomers, looking through small telescopes, mistook for the disks of distant planets. They turned out to be something much stranger. A planetary nebula is the death shroud of a sun-like star. When a star, similar to our sun, reaches the end of its life, it doesn't explode in a supernova. It expands into a red giant, then sheds its outer layers in a slow, gentle release that creates a glowing shell of gas around the dying core. The core itself eventually contracts into a white dwarf, the dense remnant that will slowly cool over billions of years. The shell of expelled gas glows because the white dwarf, despite being smaller, is incredibly hot, and its ultraviolet radiation makes the surrounding gas fluoresce. The Cat's Eye Nebula does this with extraordinary complexity. Most planetary nebulae are roughly spherical or shaped like a simple dumbbell. The Cat's Eye has nested concentric rings, knots, jets, and spiraling arcs. The pattern looks almost designed, as if some intelligence sketched it out. The complexity comes from the dying star's history. which apparently shed material in pulses over thousands of years, creating layer upon layer of expelled gas, each one a record of one of the star's death throes. The 11 concentric rings around the central nebula have been studied for decades. Each ring marks a separate ejection event, separated by roughly 1,500 years. The dying star apparently underwent rhythmic pulsations as it died, expanding and contracting and expelling gas in regular cycles. The rings are a record of those cycles. A stellar EKG written in light, the bright inner regions, with their jets and bipolar outflows, suggest the dying star is part of a binary system with a companion star whose gravity has shaped the more recent ejections into the elaborate patterns we see now. Imagine being able to read a star's biography from the structure of its nebula. The cat's eye is like a tree with rings. Each shell, each pattern, marks a moment in the star's last days. We can study it. We can date the rings. We can reconstruct with some confidence what the star did during its long death. The nebula is both a beautiful image and a historical document of a single star's specific demise. Our own sun will eventually do something similar. In about 5 billion years, when it begins to die, it will expand into a red giant, swallowing Mercury and Venus, possibly Earth. Then it will shed its outer layers, leaving behind a planetary nebula glowing for tens of thousands of years before fading. Whatever shapes that nebula takes, whatever colors and patterns emerge, will be the sun's last work of art. There will be no humans around to see it, presumably, but it will still be there. Beauty doesn't require an audience. The Helix Nebula, sometimes called the Eye of God or the Eye of Sauron, is another planetary nebula, this one about 700 light-years away. It's one of the closest planetary nebulae to Earth. From our perspective, it appears as a giant glowing ring with a complex inner structure of knots and tendrils. Photographs of it look almost unsettlingly like a giant eye staring back at us from across space. Hence, the names. The pareidolia is unavoidable. Once you see it as an eye, you can't unsee it. The Helix Nebula's central star is a white dwarf, the cooling corpse of a star that died maybe 10,000 years ago. The surrounding gas is still expanding, illuminated by the dwarf's intense ultraviolet light. The patterns we see are shaped by the dynamics of the gas, the magnetic fields, and the radiation. Yet the result, by accident, looks like a face. The universe makes patterns that look like familiar things, even when nothing intentional is happening. Inside the helix, Hubble photographed thousands of small comet-like structures called cometary knots, each one about as large as our solar system, with tails pointing away from the central star. These knots formed where denser regions of gas resisted the expanding shell, getting sculpted by the radiation into teardrop shapes. There are thousands of them inside the nebula. Each one is the size of our solar system. Each one is being slowly eroded by the central star's radiation. Each one is its own miniature work of cosmic art, sculpted by physics over thousands of years. The Crab Nebula is different. The Crab is the wreckage of an actual stellar explosion, a supernova that was witnessed and recorded by Chinese, Arabic, and possibly Native American astronomers in 1054. They saw a new star appear in the daytime sky, brighter than Venus, visible for weeks. They didn't know what they were looking at, but they recorded it, and we can match their observations to a specific star that died around then. The Chinese records describe a guest star that appeared in the constellation Taurus on the 4th of July, 1054. It was visible during the day for 23 days. At night, it was visible for nearly 2 years before fading. Imagine being a Chinese astronomer in the 11th century, looking up and seeing a star that wasn't there yesterday, one that was bright enough to see during the day. You'd have no framework for understanding what was happening. You'd just record what you saw, write it down in the imperial astronomical records, and pass the observation forward through time. 1,000 years later, we can read those records, look at the same patch of sky, and find the Crab Nebula expanding outward, exactly where the Chinese astronomers said the new star appeared. Their observation, made with the naked eye, anchors our understanding of what we see today through space telescopes. The result, 1,000 years later, is the Crab Nebula, a roughly 6 light-year wide cloud of gas expanding outward from the explosion at over 1,000 kilometers per second. Inside it, near the center, is what's left of the star that exploded, a neutron star, a city-sized object spinning 30 times every second. Beaming radio pulses at us with each rotation. A pulsar. The pulsar, at the heart of the Crab, is one of the most studied objects in astronomy. It pulses with extraordinary regularity, more accurate than most clocks, until occasionally it experiences what astronomers call glitches, where the rotation suddenly speeds up by a tiny amount. Glitches are thought to be caused by movements in the neutron star's interior, possibly involving the rearrangement of superfluid neutron matter beneath the crust. They're tiny, but they tell us something about what's happening inside an object we can never visit. The Crab Nebula is alive in a way many other nebulae aren't. Energy from the central pulsar continues to power the expanding cloud, making it glow brighter than it would if it were just gas drifting in space. The structure shifts and changes on timescales of years, visible if you compare photographs taken decades apart. The nebula is a movie, not a still photograph if you have the patience to watch it over centuries. When we look at the Crab Nebula tonight, we're seeing a star's death throes recorded 1,000 years ago by Chinese astronomers, expanding outward toward us at the speed of debris. We're looking at the past, but we're also looking at a process, death and life mixed together. The dying star is making new things possible. The atoms that were inside that star are now spreading through space, eventually destined to become parts of new stars, new planets, new life. The Crab Nebula is a stellar funeral and a cosmic seedbed at the same time. Now, let's look at something even more dramatic. Galaxies in collision. When two galaxies pass close to each other, gravity does extraordinary things. The galaxies don't just bounce off each other or merge cleanly, they tear at each other. Long streams of stars get pulled out into space, forming what astronomers call tidal tails. Star formation accelerates in the regions where gas is compressed by the encounter. The shapes that result are some of the most complex and visually striking objects in the universe. The Antennae galaxies, about 45 million light-years away in the constellation Corvus, are perhaps the most famous example. Two spiral galaxies, formerly distinct, are in the middle of a long collision that started about 200 million years ago and will continue for another 400 million years before they fully merge. From our viewpoint, the result looks like two cosmic creatures locked in an embrace, with long tentacle-like streams of stars and gas flung out behind them, hence the name. Inside the antennae, hundreds of new star clusters are forming, ignited by the collision's compression of gas. Some of those clusters will become globular clusters, dense spheres of stars that can persist for billions of years. The collision is a stellar maternity ward on a cosmic scale. The Hubble Space Telescope has photographed the antennae multiple times over the decades, each photograph revealing more detail. The cores of the two original galaxies are still distinct, even after 200 million years of merging. They orbit each other in a slow death dance, gradually spiraling closer, eventually destined to combine into a single elliptical galaxy. The whole process will take another 500 million years to complete. What's strange about galactic collisions is that, despite the visual chaos, individual stars almost never collide. Stars in galaxies are spread so thinly that even when two galaxies pass through each other, the chance of any two specific stars hitting each other is essentially zero. Two galaxies passing through each other is mostly empty space passing through empty space. The galaxies themselves get distorted and merged, but the stars within them just sail past each other unharmed. Many of the stars in the antennae will end up with new orbital paths after the merger, possibly thrown into intergalactic space, possibly captured by the merged galaxy's gravity, possibly ending up in completely different locations than where they started. But they don't crash. The exception is gas. Galaxies contain vast amounts of interstellar gas, and unlike stars, gas does collide. When two galaxies merge, their gas clouds smash together, compress, heat up, and trigger waves of new star formation. Galactic collisions are how some of the most active starburst galaxies form, with rates of starbirth dozens or hundreds of times higher than normal galaxies. The collisions don't kill stars. They make new ones. Our own galaxy will go through this. The Milky Way and Andromeda are on a collision course. In about 4.5 billion years, they'll begin to interact gravitationally, swing past each other, swing back, and eventually merge into a single elliptical galaxy. Astronomers have given the future merged galaxy a name: Milkomeda. From a hypothetical Earth, if Earth still exists then, the night sky would be filled with the bright stars and dust lanes of Andromeda gradually overlapping with our familiar Milky Way. The view would be spectacular, possibly the most beautiful sky ever seen from our planet. The merger will unfold over billions of years. First, Andromeda will slowly grow larger in our sky, going from a small fuzzy patch to a clearly visible disk, larger than the Moon, then larger than your hand at arm's length. Then the two galaxies will begin to interact. Tidal tails will stream out into space. Star formation will accelerate. The familiar shape of the Milky Way will distort. Our spiral arms tearing apart, the disk beginning to thicken and warp. By the end of the merger, the resulting Milkomeda will be a smooth elliptical galaxy with no spiral structure, just a vast egg-shaped distribution of stars. We won't be there to watch it. Earth will probably be uninhabitable by then, possibly engulfed by the dying sun. But the collision will happen. Some other observer, maybe an alien on a distant world, maybe a far future descendant of humanity living somewhere new, might look up and see what we will never see. The cosmic dance will be witnessed somewhere by someone, even if we're not there. There are many other galactic collisions visible across the sky. The Mice galaxies, two spiral galaxies near each other with long tidal tails extending into space. NGC 6872, sometimes called the Penguin Galaxy, where a small dwarf galaxy is being swallowed by a larger spiral, the combined shape looking strikingly like a penguin protecting an egg. The Cartwheel Galaxy, where a head-on collision created concentric ring structures unlike anything else in the local universe. The Cartwheel is particularly strange. About 400 million years ago, a small galaxy plunged through the center of a larger spiral galaxy at high speed. The impact sent a shockwave outward through the spiral's disk like a stone dropped into a pond, creating a ring of compressed gas that triggered massive new star formation. The result, today, is a galaxy that looks like a wagon wheel, a bright ring of new stars surrounding a dimmer hub. with the small galaxy that caused the collision still visible nearby, having passed through and continued on its way. The cartwheel won't stay this shape forever. The ring will gradually fade as the new stars age and the gas disperses. But for now, for the next few 100 million years, the cartwheel is one of the most distinctive galaxies in our cosmic neighborhood. Each collision is a beauty in itself. Each one is also a reminder that galaxies aren't fixed objects, frozen in shapes that last forever. They're dynamic, they move, they interact. The universe at the largest scales is full of constant motion and change, just slowed down to timescales that exceed any human lifespan. Let me tell you about something even more extreme. Gravitational lensing. Einstein figured out, over a century ago, that gravity bends light. If you put a massive object between yourself and a more distant light source, the gravity of the intermediate object will warp the path of the light, distorting and magnifying the image of whatever's behind it. Einstein himself thought the effect would be too small to ever observe, but he was wrong. With modern telescopes, we can see gravitational lensing all over the sky, especially around massive galaxy clusters. The first observational confirmation of gravitational lensing came during a solar eclipse in 1919. Arthur Eddington, a British astronomer, led an expedition to photograph stars near the Sun during the eclipse. According to Einstein's theory, the Sun's gravity should bend the light from those stars, making them appear in slightly different positions than where they would normally be. Eddington measured the shift, found it matched Einstein's prediction, and overnight, Einstein became one of the most famous people on Earth. The newspapers ran headlines about how gravity bends light. The picture of the universe changed. For decades, that solar eclipse measurement was the only direct evidence of gravitational lensing. Stars and galaxies didn't appear to be in the wrong places. Then, in 1979, astronomers discovered something strange. Two quasars in the constellation Ursa Major appeared to be identical twins with the same spectrum, the same redshift, the same brightness, sitting side by side in the sky. They were too similar to be coincidence. Astronomers realized they were looking at the same quasar twice, with the light from a single distant source split into two paths by the gravity of an intervening galaxy. Gravitational lensing on a cosmic scale, finally observed in the deep universe. The result, when conditions are right, is some of the strangest and most beautiful imagery the universe produces. Einstein rings are the most famous example. When a distant galaxy or quasar is perfectly aligned behind a foreground galaxy, the light from the background object gets bent into a circle around the foreground galaxy, forming a glowing ring. The ring is a kind of cosmic mirage. A single object's light split and bent into a halo by the gravity of an intervening mass. The first Einstein ring was discovered in 1988. We've since found dozens more. Each one is a moment where the geometry of the cosmos lined up precisely enough to produce this strange optical phenomenon, and we happen to be looking from the right angle to catch it. Slight misalignment, and the ring becomes an arc, or just a few stretched smears. Perfect alignment, and you get the full ring, a perfect circle of light around a galaxy. Galaxy clusters can produce even more extreme lensing. The mass of an entire cluster, hundreds or thousands of galaxies, plus the surrounding dark matter, bends light from background galaxies into long arcs, multiple images, and bizarre distortions. Photographs of the Abell 1689 cluster show dozens of arcs and ring fragments around it. Each one a magnified, distorted view of a galaxy far behind the cluster. The Hubble Frontier Fields project, conducted between 2013 and 2017, used Hubble to photograph 6 massive galaxy clusters in extreme detail, taking advantage of their gravitational lensing to look deeper into the universe than would otherwise be possible. The resulting images showed thousands of magnified background galaxies, including some of the most distant galaxies ever observed. Without the lensing, those galaxies would have been too faint to detect. With it, they became visible, their light boosted by the cosmic magnifying glass of intervening dark matter. In some cases, gravitational lensing has let us see galaxies so distant that, without the lensing magnification, we couldn't have detected them at all. The lensing acts as a natural telescope, multiplying the power of our actual telescopes. Astronomers use it to study the most distant, earliest galaxies in the universe, ones that existed only a few 100 million years after the Big Bang. There's an even more remarkable phenomenon called a quadruple image lens, sometimes called an Einstein cross. When a background galaxy or quasar is positioned just slightly off the perfect alignment, the gravitational lens splits its light into 4 separate images arranged around the foreground lensing galaxy, looking like a cross or a diamond pattern. The most famous example is the Einstein cross itself, discovered in 1985, where a distant quasar appears as 4 nearly identical bright spots around a closer galaxy. Each spot is the same quasar, seen from the same angle, but with the light arriving via 4 different paths around the foreground galaxy's gravity. 4 photographs of one object, taken at the same instant, separated by tiny differences in the path the light traveled to reach us. The beauty here is multiple. The visual beauty of the lensing patterns themselves, arcs and rings and twisted images. The intellectual beauty of understanding that the geometry of space-time can act as a lens. The poetic beauty of using one ancient galaxy to magnify an even more ancient one. Looking through one piece of history to see another, deeper history. Einstein, thinking about his equations a century ago, predicted this. He was right, even when he didn't think we'd ever observe what he predicted. The universe operates by mathematical rules elegant enough that simple equations, written on a page in 1915, accurately describe phenomena we couldn't observe until decades later. The fact that the universe is comprehensible at all, that we can predict its strange behaviors before we see them, is itself a kind of beauty. Now, let me take you to one of the most stunning recent images we've captured. The Carina Nebula. About 7,500 light-years from Earth, in the southern constellation Carina, lies a vast star-forming region that's home to some of the most massive stars in our galaxy. The Hubble Space Telescope photographed parts of it years ago, but the James Webb Space Telescope has given us new views that exceed anything previously imaginable. The most famous Webb image of Carina, released in 2022, shows what's been called the cosmic cliffs, a region of the nebula where dense clouds of gas and dust are being eroded away by the radiation from young, massive stars hidden beyond the cliffs. The image shows what looks like a mountainous landscape, with peaks and valleys glowing in cosmic colors, and stars scattered across the scene like jewels. What you're actually looking at is a wall of gas and dust about 7 light-years tall. The wall is being slowly evaporated by the energy from young stars in the surrounding region. As the gas heats up, it gets pushed outward and then drifts upward into the cooler space above the wall. The result, in infrared light captured by Webb, is a structure that looks remarkably like Earth landscapes. The cliffs and mountains are made of gas, but the visual analogy is irresistible. We can't help seeing terrestrial features in cosmic patterns because we're built to recognize landscape. The nebula contains hundreds of newly formed stars, plus ongoing star formation that will continue producing new stars for thousands of years. Webb's infrared sensitivity penetrates the dust that hides much of the nebula in visible light, revealing the bright cores of dozens of young stars throughout the structure. Some of these stars are still in the early stages of formation, surrounded by protoplanetary disks where, possibly, planets are forming right now. Each disk is a future solar system. Each one might host life eventually. Each one is a kind of nursery for the next generation of cosmic complexity. Beyond the cosmic cliffs, deeper in the Carina Nebula, are some of the most interesting stars in our galaxy. Eta Carinae is one. It's a binary system containing a star that's possibly the most massive in the Milky Way, weighing over 100 times the mass of our Sun. It's unstable. It periodically experiences enormous outbursts, ejecting huge amounts of material into space. In 1843, Eta Carinae experienced what astronomers call the Great Eruption, becoming temporarily the second brightest star in the entire night sky, despite being 7,500 light-years away. The eruption shed enough material to form a beautiful expanding nebula around the star called the Homunculus Nebula, which we can still see today. The Great Eruption was witnessed by people on Earth in 1843. They didn't know what they were seeing. They watched a star get brighter and brighter, becoming one of the most prominent stars in the sky and then slowly fade. The eruption lasted about 20 years before the star returned to something closer to normal. Now, when we point the Hubble or Webb at Eta Carinae, we can see the expanding cloud of material that the star ejected during that eruption, still spreading outward into space at hundreds of kilometers per second. The Homunculus Nebula has two distinct lobes of expanding gas, looking like a pair of cosmic balloons, with the bright central star nearly hidden behind the dust. Eta Carinae will probably go supernova in the near astronomical future, possibly within the next million years. When it does, it'll be one of the most spectacular events visible from Earth. The supernova will be visible during the day, brighter than the moon, possibly bright enough to read by at night. Anyone alive to see it will witness one of the rarest astronomical events in human history. A nearby star, WR 104, has been the subject of speculation about whether its eventual supernova might pose a danger to Earth. The star is in the constellation Sagittarius, about 8,000 light-years away. It's a Wolf-Rayet star, the kind that's expected to end its life in a particularly violent supernova that produces a gamma-ray burst. Some early calculations suggested WR104 might be aimed almost directly at Earth, which could mean a powerful gamma-ray burst would hit us when it explodes. More recent observations suggest the star is probably angled slightly away from us, which would minimize any potential impact. But it's a reminder that the universe contains real, present dangers as well as beauties. The same processes that make beautiful nebulae also make explosions that could potentially harm life on Earth, given the right alignment. The Carina Nebula contains many such stories. Multiple massive stars, each one a future supernova. Each one, in dying, will sculpt the surrounding gas, blowing bubbles, creating new structures, possibly triggering the formation of more stars. The nebula isn't a static beauty. It's a beauty in motion, slow enough that humans don't see it move, but moving nonetheless. Let's leave the gas and dust. Let's look at the most beautiful single objects in the universe at large scales, galaxies. The Sombrero Galaxy is perhaps the most photogenic galaxy in the night sky. It's about 30 million light-years from Earth, in the constellation Virgo. From our angle of view, we see it almost edge-on, which gives it a distinctive flat disk with a bright central bulge, looking remarkably like a wide-brimmed Mexican hat, hence the name. What makes the sombrero so striking is the dust lane that wraps around the disk. Dark, sharply defined, it traces the spiral arms of the galaxy, even though we can't see the spiral structure directly because of our viewing angle. The contrast between the bright bulge, the glowing disk, and the dark dust lane makes the sombrero look almost designed. It's the kind of image that, if you didn't know it was a real photograph, you'd assume was a rendering or a painting. The sombrero contains roughly 2,000 globular clusters, 10 times more than the Milky Way has. Globular clusters are dense, ancient spheres of stars, some of the oldest objects in any galaxy, dating back nearly to the formation of the universe itself. The sombrero's vast collection of them suggests it's an old galaxy with a complex history, possibly formed through the merger of several smaller galaxies billions of years ago. Inside the sombrero is a supermassive black hole, perhaps 1 billion times the mass of our Sun. This is one of the largest black holes known in our cosmic neighborhood. The galaxy itself is a strange hybrid. It has features of both spiral and elliptical galaxies, and astronomers are still arguing about how to classify it. Whatever its category, it remains one of the most beautiful single objects in our local universe. Then there's NGC 1132, the Tadpole Galaxy, a spiral galaxy with a long stream of stars and gas trailing behind it, a tail extending nearly 300,000 light-years into space. The tail is the result of a gravitational interaction with another galaxy that passed through the tadpole hundreds of millions of years ago. The encounter pulled stars and gas out into space, forming the stream we see today. The tail will eventually disperse, the stars will redistribute themselves, but for now, the tadpole is a striking visual reminder that galaxies are not isolated objects. They interact, they merge, they distort each other, and the results are sometimes hauntingly beautiful. The Whirlpool Galaxy, another classic, is a face-on spiral about 23 million light-years away. Because we see it from above, we can see its spiral arms in their full glory, complete with bright pink star-forming regions, dark dust lanes, and a smaller companion galaxy interacting with it gravitationally. The Whirlpool is a textbook example of what a spiral galaxy looks like, and it's the kind of object that inspires people to study astronomy in the first place. There's a particular Hubble image of the Whirlpool that hangs on millions of dorm room walls and computer desktops, and for good reason. It's one of the most striking galaxy images ever captured. The smaller companion galaxy, NGC 5195, is being slowly consumed by the Whirlpool. The two galaxies have been interacting for hundreds of millions of years, and the gravitational tug is what makes the Whirlpool's spiral arms so prominent and well-defined. Without the companion, the Whirlpool's arms would be more diffuse, more typical. The interaction is what gives this particular galaxy its iconic shape. Eventually, NGC 5195 will be fully absorbed, and the Whirlpool will gradually lose the sharp definition of its arms. The textbook image will become outdated, given enough cosmic time. But for now, the geometry is perfect. The Pinwheel Galaxy, also called Messier 101, is another beautiful face-on spiral about 21 million light-years from Earth. It's significantly larger than the Milky Way, with a diameter of about 170,000 light-years compared to our galaxy's 100,000. Hubble's image of the pinwheel, released in 2006, was at the time the largest and most detailed photograph ever taken of a spiral galaxy by Hubble. The image shows millions of individual stars, vast dust lanes, glowing regions of hydrogen gas where new stars are forming, and the overall pattern of the spiral arms wrapping around the bright central bulge. Our own galaxy, the Milky Way, is also a spiral. We can't see its full structure from our position inside it, but we can map it through careful observation, and we know it's a barred spiral with multiple arms, somewhat similar in structure to the Whirlpool or the Andromeda Galaxy. From outside, the Milky Way would look very much like one of those famous photographs. A spiral arm we sit in, a central bulge with a supermassive black hole, dust lanes, and a faint halo of older stars surrounding the disk. Beautiful. In the same way, other spiral galaxies are beautiful, just from a perspective we can't achieve. There's a thought experiment astronomers sometimes engage in. What does our galaxy look like from outside, really? We have models, we have simulations, but we've never been outside it. Probably never will be. The view is forever beyond us. We can only look at other galaxies and infer that ours might look similar. Our home is a wonder we'll never see directly. We have to imagine it. The closest we can come is to look at the band of the Milky Way stretched across a dark sky, away from city lights, and understand that we're seeing the disk of our own galaxy edge on from inside. That dim, milky band is the combined light of hundreds of billions of stars, most of them too faint to see individually, blurred together into a luminous river. We're inside the river, looking sideways through it. From a different angle, we'd see the whole disk spread out as a circle. From outside, we'd see the spiral structure. But we can never get there. We have to be content with the view from inside. Now, let me show you something truly massive. Galaxy clusters and superclusters. A galaxy cluster is a gravitationally bound collection of galaxies, sometimes hundreds, sometimes thousands of them, orbiting each other in a vast cosmic dance. The Virgo cluster, the nearest large cluster to our own galaxy, contains about 2,000 galaxies. The Coma cluster, farther away, contains thousands. These are the largest gravitationally bound structures in the universe. Photographs of galaxy clusters are unlike anything else in astronomy. Looking at an image of the Coma cluster, you see hundreds of galaxies of various shapes and sizes scattered across the field of view, like a city of cosmic islands. Some are spirals, some are ellipticals, some are merging. Each one contains hundreds of billions of stars. The total number of stars visible in a single cluster image is staggering, more than humans could ever count. The dominant galaxies in clusters are usually giant ellipticals formed by the mergers of multiple smaller galaxies over billions of years. NGC 4893, sometimes called the Bullet Cluster, is one of the most famous galaxy clusters because of what it revealed about dark matter. Two clusters collided, and the gas of each cluster slowed down due to friction with the other cluster's gas, while the dark matter passed through unaffected. By mapping the gravitational lensing patterns around the colliding clusters, astronomers found that the bulk of the mass was offset from the visible gas, exactly where dark matter would be expected to be. The Bullet Cluster is some of the strongest evidence we have for the existence of dark matter. The Hubble Deep Field photograph showed us how full the universe is at every scale. In a tiny patch of sky, smaller than a grain of sand held at arm's length, Hubble found over 3,000 galaxies. The James Webb Space Telescope's deep field images find even more, going deeper, seeing fainter and older galaxies. The universe at the deepest scales is overwhelmingly populated. Everywhere we look, more galaxies, everywhere. In 1995, when Hubble first photographed the deep field, the result was so unexpected that the data was carefully reanalyzed before it could be released. The astronomers couldn't believe how many galaxies appeared in such a small region of empty sky. The image is now famous as the Hubble Deep Field, and it shows now truly empty regions of sky. Everywhere we point our deepest telescopes, we find more galaxies packed densely across cosmic distance. The Hubble Ultra Deep Field, taken in 2004, went even deeper. The Hubble Extreme Deep Field, in 2012, deeper still. Each iteration found more galaxies, fainter and older, going back closer to the Big Bang. Webb has now extended this further, capturing galaxies that existed when the universe was less than 500 million years old. The earliest galaxies, just barely visible at the edge of what's possible to detect, appear as small smudges of red light, their wavelengths stretched by the expansion of space across nearly 14 billion years. If you had infinite time and infinite computing power, you could create a star map of the entire observable universe, 2 trillion galaxies, each one with hundreds of billions of stars, quintillions of stars total, each of them potentially with planets, each of them potentially with life. The numbers exceed comprehension, and yet, when we photograph these distant clusters and superclusters, the images are, against all expectation, beautiful. The galaxies arrange themselves into filaments and walls, with vast cosmic voids between them. The structure of the universe, at the largest scales, has been called the cosmic web. It's a network of luminous threads in the dark, with empty spaces between, looking strangely organic, as if the universe itself is a kind of cosmic organism, with a circulatory system of bright matter through dark space. Computer simulations of the cosmic web, based on our best understanding of dark matter and gravity, produce structures that match remarkably well with what we observe. The simulations look like nervous systems, or root networks, or fungal mycelia. The patterns are strikingly similar to biological systems, even though there's no biology involved, just gravity and matter, organizing themselves over 14 billion years. Why does the universe at the largest scales resemble biological structures? The answer involves how gravity works in an expanding universe with dark matter. The early universe was nearly uniform, with tiny density variations. Slightly denser regions attracted more matter through gravity, growing denser still. Slightly less dense regions lost matter to their neighbors. Over billions of years, the slight initial differences amplified into the cosmic web we see today, dense filaments where most of the galaxies live, and vast voids where almost nothing exists. The same kind of branching, networked patterns that emerge from many natural processes, including biological growth, also emerge from cosmic structure formation. The universe and a tree, in some abstract sense, are obeying similar mathematical principles of network formation in growing systems. The largest known structure in the universe is the Hercules Corona Borealis Great Wall, a galactic supercluster filament about 10 billion light-years across. It contains an enormous number of galaxies. We don't fully understand how something this large could have formed, given the standard cosmological model. The structure is, in some ways, too big to exist, according to our current physics. But it does exist. We can see it. We can map it. The wall is real. And from our viewpoint, looking out across space, the cosmic web itself is one of the most beautiful structures in existence. Not a single object, not a star or a galaxy or a nebula. The entire structure of the universe, mapped out as a glowing pattern, is itself a work of cosmic art. Let me tell you about a few specific phenomena that don't fit into the usual categories but are worth their own mention. Aurorae on Jupiter. The largest planet in our solar system has the most powerful auroras anywhere we know of. Jupiter's auroras are caused by its incredibly strong magnetic field, by far the strongest of any planet in our solar system, which channels charged particles down to the polar regions and creates light shows that can be hundreds of times more energetic than Earth's auroras. The Hubble Space Telescope and the Juno spacecraft have photographed Jupiter's auroras in ultraviolet and infrared light, revealing structures of staggering complexity. Glowing rings, ovals, polar storms of light, The visual is alien, beautiful, and reminds us that Earth isn't the only place in the cosmos where the sky burns with color. Jupiter's auroras are also continuously powered by the volcanic moon Io. Io is the most volcanically active body in the solar system, constantly erupting and ejecting material into space. Some of that material gets ionized by Jupiter's radiation belts and channels along the planet's magnetic field lines, eventually slamming into the Jovian poles and producing auroras that never go quiet. Earth's auroras come and go with solar activity. Jupiter's are always burning, fed by the constant volcanic output of one of its moons. The light shows are perpetual. The Juno spacecraft, in orbit around Jupiter since 2016, has photographed Jupiter's poles in unprecedented detail. The images show vast polar storms surrounded by smaller cyclones, all swirling in patterns unlike anything on Earth or any other planet. The poles look almost like geometric mosaics of storms, each one larger than entire continents on Earth. The visual is so unfamiliar that it took astronomers months to develop language for what they were looking at. Saturn's hexagonal storm. At Saturn's North Pole, there's a permanent atmospheric structure shaped like a perfect hexagon. The hexagon is roughly 30,000 kilometers wide, larger than Earth, and has been observed continuously since the 1980s. The shape is so geometric, so precise, that early photographs led some people to suspect it was an optical illusion or a processing artifact. It isn't. It's a real fluid dynamics phenomenon, where the jet stream around the pole forms standing waves that produce the hexagonal pattern. The mechanics are well understood, but the visual remains startling. A perfect hexagon, larger than our planet, on the top of a gas giant. A pattern Mother Nature painted with wind and pressure, stable for decades. The hexagon's color shifts over time. When Cassini first observed it closely in the early 2000s, the hexagon was a deep blue. As the seasons changed on Saturn, with each Saturnian year lasting about 30 Earth years, the hexagon shifted to gold. The seasonal color change is thought to be related to atmospheric chemistry that varies with the angle of sunlight on the pole. Saturn has long seasons, and the hexagon experiences each season slowly, evolving its colors over decades. Comet tails. When a comet approaches the sun, the heat causes its frozen surface to evaporate, releasing gas and dust that gets blown away from the sun by the solar wind, forming a long tail, or sometimes multiple tails. The most famous comets in human history have all been visually striking. Halley's Comet, returning every 76 years, has been observed for thousands of years. Comet Hale-Bopp in 1997 was visible to the naked eye for over a year. Comet Neowise in 2020 was a recent return to the era of bright comets visible without telescopes. Halley's Comet has been observed at every appearance since at least 240 BCE, when ancient Chinese astronomers recorded its passage. The Bayeux Tapestry, depicting the Norman conquest of England in 1066, shows the comet appearing during the conflict. Mark Twain was born during one passage of Halley's Comet in 1835, and famously predicted he would die during its next return. He was right. He died in 1910, during Halley's next appearance. The comet has accompanied human history through dozens of returns, watched by every generation of human civilization. Comet Hale-Bopp was particularly memorable. Discovered in 1995 by amateur astronomers, it became one of the brightest and longest visible comets in modern history. For over a year, it was visible to the naked eye, with two distinct tails, a blue gas tail and a curved white dust tail, stretching across the sky. The comet passed through human consciousness during a strange cultural moment in the mid-90s, and unfortunately became associated with a tragedy when a UFO cult committed mass suicide, claiming the comet was being followed by an alien spaceship that would take them to the next level of existence. The comet itself, of course, was just a comet, a frozen ball of ice and dust, doing what comets do. The visual of a comet against the night sky is a kind of fragile, temporary beauty. The comet itself is a small object, only a few kilometers across. The tail is millions of kilometers long, but it's almost vacuum, just a thin trace of gas glowing in sunlight. The whole structure is ephemeral. It exists only when the comet is close to the sun, and dissipates when the comet moves back out into the cold dark. The same comet, returning a century later, will look different. Different gas, different dust, different appearance. Each apparition is a unique work of cosmic art, performed once and then dispersed. Now let me return to nebulae for a moment, because there are a few more that deserve attention. The Tarantula Nebula is a star-forming region in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 160,000 light-years away. It's the largest and most active star-forming region in our local group. The Webb telescope's photograph of the tarantula, released in 2022, shows a vast network of glowing gas and dust, with thousands of newborn stars visible throughout the structure. The image is one of the most detailed views of star formation we've ever obtained, and it's stunning. The colors range from deep red to bright white, with intricate filaments and bubbles carved by the radiation of the young stars. Inside the tarantula is a cluster of stars called R136, which contains some of the most massive stars known. One of those stars, R136, a 1, is estimated at over 200 solar masses, possibly the most massive single star ever found. Eventually, that star will explode in a supernova so powerful that it might leave behind a black hole instead of a neutron star. The tarantula is a stellar nursery and a stellar mortuary at the same time, with new stars being born and old ones racing toward their deaths. If a supernova goes off in the tarantula, which they do regularly given the number of massive stars there, the resulting shockwave triggers more star formation in the surrounding gas. The nebula is a self-sustaining stellar nursery. Each generation of stars makes more stars possible by stirring up the gas. The Veil Nebula is another beautiful object, a supernova remnant about 2,400 light-years from Earth in the constellation Cygnus. The supernova that created it exploded 10 or 20,000 years ago, and the expanding shockwave is still visible today as a complex network of glowing filaments. Photographs of the veil showed delicate, thread-like patterns in red and blue and green, looking almost like watercolor paintings of cosmic scale. The patterns are the result of the shockwave hitting different densities of gas in interstellar space, with different elements glowing in different colors. The veil is so large in our sky, despite being 2,400 light-years away, that it covers an area about 6 times the diameter of the full moon. Most amateur astronomers can see parts of it through a small telescope, especially with the help of nebula filters that highlight the specific wavelengths emitted by the glowing gas. The veil is one of the most accessible deep sky objects for backyard astronomy, a beauty that you can witness with relatively modest equipment. The Trifid Nebula combines 3 different types of nebulae in one beautiful object. It contains an emission nebula, which glows red from hydrogen, ionized by hot young stars. It contains a reflection nebula, which glows blue from light, reflecting off cold dust. And it contains a dark absorption nebula, which appears as black lanes cutting through the bright regions. The combination of all 3 in one object is unusual, and the visual contrast is striking. Trifid sits about 5,000 light-years from Earth in the constellation Sagittarius. The Lagoon Nebula, near the Trifid in the same direction in the sky, is another star-forming region with active new stars and complex gas structures. Together with the Trifid, the lagoon forms one of the most photogenic regions of the southern Milky Way, a favorite target for amateur astronomers and professional observatories alike. The Orion Nebula, perhaps the most famous nebula visible to the naked eye, sits about 1,300 light-years from Earth, in the constellation Orion just below the three stars of Orion's belt. On a dark night, you can actually see the nebula as a faint smudge in the middle of the Orion's sword. Through a telescope, even a small one, the nebula reveals itself as a glowing cloud of pink and green and blue with bright stars embedded throughout. It's one of the closest stellar nurseries to Earth, and it's been studied by astronomers for centuries. Galileo himself observed it. Now it's photographed in extraordinary detail by Hubble and Webb, revealing structures that earlier generations of astronomers could only dream of. At the heart of the Orion Nebula is a small group of bright stars called the Trapezium Cluster. These four bright stars, surrounded by hundreds of fainter ones, are responsible for illuminating the surrounding gas and shaping the nebula's structure. The brightest of the four is so hot that its ultraviolet radiation is gradually evaporating the gas around it, eroding the nebula from within. The Orion Nebula won't last forever in its current form. The bright young stars at its core are slowly destroying the nursery that produced them. Each of these nebulae is its own world, its own work of art, its own narrative of stellar birth and death. None of them are static. All of them are changing on cosmic timescales, slowly enough that we don't see the change in our lifetimes, but it's happening. Beauty in the universe is dynamic, even when it appears to be still. Let me mention a few of the rarest beauties. Let me take you somewhere we've never been, but can now imagine in detail: the exoplanets. Until 1995, we knew of no planets outside our solar system. The first confirmed exoplanet around a normal star, 51 Pegasi b, was discovered that year. Since then, we've catalogued over 5,000 exoplanets, with thousands more candidates waiting to be confirmed. Most of them are very different from anything in our solar system. Hot Jupiters, gas giants larger than Saturn but orbiting closer to their star than Mercury, orbits our Sun, with surface temperatures over 1,000 degrees. Super-Earths, rocky planets larger than Earth but smaller than Neptune, of which we have no example in our own neighborhood. Tidally locked worlds, where one side faces the star permanently in eternal day, while the other side faces away in eternal night. The TRAPPIST-1 system, about 40 light-years from Earth, is one of the most fascinating discoveries. It contains 7 Earth-sized rocky planets orbiting a small, cool red dwarf star. 3 of those planets are in the habitable zone, where liquid water could potentially exist on the surface. The 7 planets orbit in a complex resonance, their orbital periods locked into ratios that make the whole system gravitationally stable. From the surface of any of those planets, the others would appear as visible disks in the sky, sometimes larger than our moon. Imagine looking up at night and seeing not stars in the distance, but other worlds, close enough to see their continents and weather patterns. We don't have surface photographs of any exoplanet, and we won't have them for the foreseeable future. Our telescopes can detect planets, measure their sizes, sometimes determine their atmospheric compositions, but actually photographing the surface of a world around another star requires capabilities we haven't built yet. What we have are artistic interpretations, generated by NASA artists based on the limited data we have, showing what these worlds might look like. Some are clearly Earth-like. Some are ocean worlds, covered entirely in water. Some are lava worlds with surfaces of molten rock. Some are ice worlds where the surface is frozen but liquid oceans hide beneath. The diversity is staggering. The galaxy contains, by current estimates, hundreds of billions of planets. Some fraction of them are in habitable zones around their stars. Some smaller fraction probably have liquid water on their surfaces. Some smaller fraction still might have life. The numbers are so large that even tiny percentages produce enormous absolute counts. There are probably millions of habitable worlds in our galaxy alone. Probably some of them have life. Possibly some of them have intelligent life. We don't know yet. We may never know. But statistically, we're not alone. Each of those distant worlds has its own beauty, its own sunsets and sunrises, its own oceans, possibly, its own clouds, possibly, its own auroras, possibly, its own moons, casting their own shadows during eclipses. The universe is making beautiful worlds at scale, all the time, almost everywhere we look. And we, on this small blue planet, are the first generation of humans capable of detecting them. Now, let me talk about the closer worlds, the ones we've actually visited. Mars, the red planet, our nearest planetary neighbor and the most likely place beyond Earth where humans will eventually walk. Mars has been photographed by orbiters and rovers for decades, and the images coming back have grown progressively more beautiful as our cameras have improved. The Curiosity rover, the Perseverance rover, the InSight lander, all have sent back photographs of Martian landscapes that look both alien and familiar. Red dust, rocks, mountains in the distance. A thin atmosphere with high cirrus clouds. Sunsets that, due to the way Martian dust scatters light, appear blue rather than red. The blue sunset of Mars is one of the most haunting images returned by any space mission. The Curiosity rover photographed one in 2015, showing a small white sun setting behind a blue glow on the horizon, the rest of the sky in dim red dusk. The colors are inverted from Earth, where sunsets are red and the sky is blue. On Mars, the sunsets are blue and the sky is red. A reminder that beauty on other worlds doesn't have to look like Earth. The same physics, applied to different atmospheres, produces different visual results. Mars also has Olympus Mons, the largest volcano in the solar system, 22 kilometers tall, 3 times higher than Mount Everest. It's so wide that, if you stood on its summit, you wouldn't be able to see the edges. The curvature of Mars itself would hide the volcano's flanks below the horizon. Mars has Valles Marineris, a canyon system that, if placed on Earth, would stretch from New York to Los Angeles. It's deeper than the Grand Canyon and many times longer. These features have existed for billions of years, formed when Mars was still geologically active. They wait for us, frozen in time, ready to be visited eventually. Some future generation will probably stand on Olympus Mons, probably take photographs from inside Valles Marineris, probably watch a blue Martian sunset in person. The beauty is already there. We just haven't quite reached it. The moon, our own moon, has its own quiet beauty. Apollo missions in the late 1960s and early 1970s brought back over 800 pounds of moon rocks, and we have detailed photographs of nearly every region of the lunar surface. The lack of atmosphere makes the views sharp and stark. Shadows on the moon are dark in a way they aren't on Earth, where atmospheric scattering softens everything. On the moon, light and dark are absolute. Nothing in between. The Earth, viewed from the moon, is one of the most famous images in human history. The Earthrise photograph, taken by Apollo 8 astronauts in 1968, showing our blue planet rising over the grey lunar surface, has been called the most influential environmental photograph ever taken. It changed how humans thought about themselves. We saw, for the first time, that we lived on a small, fragile sphere in the dark of space, and that the moon, by contrast, was a stark, grey world with no life. That visual contrast helped launch the modern environmental movement. Beauty has consequences. Sometimes, a single photograph changes the course of human civilization. Solar eclipses, viewed from a place where the alignment is perfect, are among the most dramatic visual experiences a human can have. The moon passes in front of the sun, blocking its light, revealing the corona, the outer atmosphere of the sun, normally hidden by its overwhelming brightness. The corona looks like a glowing crown of pearl-white light, extending out from the dark disk of the moon, with delicate streamers reaching into space. People who've witnessed total solar eclipses describe the experience as transformative. Animals fall silent. The temperature drops noticeably. The world goes dark in the middle of the day. And in the sky, where the sun should be, there's an alien glow that you can look at directly for the brief minutes of totality. The reason this is possible at all is one of the more remarkable coincidences in our solar system. The sun is about 400 times larger than the moon, but it's also about 400 times farther away. From Earth's perspective, they appear to be roughly the same size. This is what allows total solar eclipses to happen at all, with the moon perfectly covering the sun's disk. Other planets have moons, but no other planet in our solar system has a moon that produces eclipses this perfect. In a billion years or so, the moon will have drifted slightly farther from Earth, and total eclipses will no longer be possible. We're alive during a particular cosmic moment when the geometry happens to work out. The corona itself is one of the great mysteries of solar physics. Despite being far above the sun's surface, it's hotter than the surface itself, sometimes by more than 100 times. The surface of the sun is about 6,000 degrees. The corona is over 1,000,000 degrees. How can the outer atmosphere be hotter than the underlying surface? Heat should flow from hot to cold, not the other way around. The answer involves complex magnetic field interactions that physicists are still working out, with recent observations from spacecraft like the Parker Solar Probe providing new data. But the corona, this hot outer atmosphere, is invisible to us most of the time, drowned out by the sun's photosphere. Only during a total solar eclipse, when the moon perfectly blocks the photosphere, can we see the corona directly. The eclipse reveals what's normally hidden. For ancient cultures, eclipses were terrifying events. The sun was being devoured. Something had gone catastrophically wrong with the cosmos. People would bang pots and pans, shout, perform rituals, anything to drive away whatever was eating the sun. When the eclipse ended and the sun returned, the rituals were credited with success. Across many cultures, eclipses were associated with omens, prophecies, the deaths of kings, the births of saviors. Records of eclipses, written down by ancient astronomers, are now used by modern historians to date specific events in human history with great precision. We know exactly when ancient eclipses happened, because the math of celestial mechanics is precise enough to predict them backward in time. Knowing when an eclipse occurred during a specific historical event helps us pin down the date of that event, sometimes accurately to within a single day, even thousands of years later. Eclipses, the events that ancient people thought were chaotic and supernatural, turn out to be among the most precise clocks in the historical record. Lunar eclipses, less dramatic, are still visually beautiful. When Earth's shadow falls on the moon doesn't disappear entirely. Some sunlight still reaches it, having passed through Earth's atmosphere, where the blue light is scattered out and the red light is allowed through. The result is a moon that turns deep red or copper-colored during a total lunar eclipse, glowing like a bloody coin in the sky. The phenomenon has been called a blood moon throughout history, and it's been associated with omens, prophecies, and superstitions across many cultures. The transit of Venus is rarer still. Venus passes in front of the Sun, from Earth's perspective, only about twice a century, and the transits come in pairs separated by 8 years, with over 100 years between pairs. The next transit pair is in 2117 and 2125. Most people alive today won't see another. The transit looks like a small black dot crawling slowly across the bright disk of the Sun, taking several hours from start to finish. Historically, transits of Venus have been used to measure the size of the solar system. The 18th century explorations to observe them led to some of the great voyages of scientific discovery. Captain James Cook's first voyage to the Pacific in 1768, which led to the European discovery of Australia and New Zealand, was originally undertaken to observe the transit of Venus from Tahiti. Astronomers had calculated that simultaneous observations from widely separated points on Earth could be combined to determine the absolute distance from Earth to the Sun, a number nobody at that time knew. Cook's expedition was one of several around the world that contributed to the calculation. The result was a vastly improved understanding of the size of the solar system. The transit of a small dark dot across the face of the Sun helped humans figure out how far they were from their own star. Transits of other planets are even rarer. Mercury transits the Sun more frequently than Venus, but only about 13 or 14 times per century. The other planets are too far from the Sun to ever transit it, from our viewpoint. Transits of distant exoplanets, however, are how we discover most of the worlds we know about beyond our solar system. When a planet passes in front of its star, from our angle, we see a tiny dimming of the star's light. By measuring those dimmings, astronomers have catalogued thousands of planets around other stars. The same physical principle that made Cook's voyage worth taking now gives us a galactic exoplanet census. Each of these alignments and events is a moment when geometry produces beauty. The cosmos arranges its various pieces in a particular configuration, and we, in our small windows of attention, get to see the result. We don't make these events happen. We just witness them, sometimes for centuries, sometimes for minutes. The privilege of being alive during these moments is part of what makes them precious. Let me tell you about something humans made that's now traveling through interstellar space. The Voyager spacecraft. Voyager 1 launched in 1977, and Voyager 2 launched the same year, just a few weeks earlier on a different trajectory. They were sent to study the outer planets, and they did, photographing Jupiter and Saturn in unprecedented detail, then continuing to Uranus and Neptune. After completing their planetary missions, they kept going, traveling outward through the solar system, eventually crossing the heliopause, the boundary where the Sun's influence ends and interstellar space begins. Voyager 1 crossed in 2012. Voyager 2 followed in 2018. They are the most distant human-made objects in existence. Both spacecraft carry a golden record, a phonograph record made of gold-plated copper with engraved instructions for how to play it in case any alien civilization ever finds them. On the records are sounds and images from Earth, greetings in 55 languages, music from various cultures and historical periods, images of human activities, photographs of the planet, recordings of natural sounds. The records are intended as a message in a bottle thrown into the cosmic ocean with no expectation that anyone will ever find them, but with the hope that just possibly Someone might. The golden record is not exactly an astronomical beauty. It's a human artifact, but it's now part of the cosmos. It's traveling through interstellar space at over 35,000 miles per hour. It will continue traveling, essentially forever, long after Earth is gone, long after our sun has died. The Voyager spacecraft will outlast our species. They will outlast our planet. They will outlast the sun. In billions of years, when the sun has expanded into a red giant and consumed Earth and faded into a white dwarf, the Voyagers will still be drifting through the dark, carrying their golden records, a small artifact of human civilization preserved in the cold of space. That's a kind of beauty too, not visual beauty, the beauty of permanence. We, brief and small, sent something out that will last longer than anything else we've ever built. The pyramids will erode, cities will crumble, continents will reshape, but the Voyager spacecraft, drifting through interstellar space, will keep going. They are humanity's longest-lasting works of art. Pioneer 10 and Pioneer 11, the spacecraft that preceded Voyager, are also drifting through interstellar space, each carrying a plaque with engraved images of humans. The New Horizons spacecraft, after photographing Pluto in 2015, will eventually leave the solar system too. 5 human-made objects slowly making their way out into the galaxy, each one a kind of beautiful gesture toward the future. Now, let me tell you about a truly recent breakthrough. The first photograph of a black hole. For most of astronomical history, black holes were theoretical objects. We could detect them indirectly by their gravitational effects on nearby stars or on light from background objects. We could see what happened around them, the accretion disks of glowing gas being pulled in. But we couldn't see them directly. By definition, light cannot escape from a black hole. Photographing one seemed impossible. Then, in 2019, the Event Horizon Telescope project announced the first direct image of a black hole. The image showed the supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years away. The photograph showed a bright orange ring of glowing gas with a dark shadow at the center. The shadow being the black hole itself, where light gets bent around but cannot escape. The image was produced by combining data from radio telescopes around the world, working in unison to create the equivalent of a planet-sized telescope. The result was the first time humans had ever seen a black hole's silhouette directly. In 2022, the same project released an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy, about 26,000 light-years from Earth. The image looks similar to the M87 photograph, with a bright ring around a dark center, though the geometry is different because Sagittarius A star is much closer and has a different mass. We have, for the first time, looked at the heart of our own galaxy and seen what's there. A black hole, 4 million times the mass of our sun, sitting at the gravitational center of all the stars in the Milky Way. The image is beautiful in a strange way. It's not a typical astronomical photograph. There are no stars, no nebulae, no galactic detail, just a glowing ring around a black void. But the meaning is staggering. We're looking at an object that bends space-time, where time itself slows to nothing at the boundary, where the laws of physics break down. We're looking at a hole in the fabric of the universe, and we're seeing it directly for the first time in history. Around supermassive black holes, when matter is actively falling in, the result is what astronomers call a quasar. Quasars are the brightest objects in the universe. They outshine entire galaxies. They are powered by the friction of gas and dust spiraling into a supermassive black hole, heating up to such extreme temperatures that the matter glows brighter than billions of stars combined. The most distant quasars we've found existed when the universe was less than 1 billion years old. They are signposts pointing back toward the early cosmos, beacons that allow us to study the conditions of the universe shortly after the Big Bang. Active quasars produce relativistic jets, beams of charged particles ejected at nearly the speed of light from the regions just outside the black hole's event horizon. These jets can extend for thousands or millions of light years, far beyond the host galaxy, painting cosmic patterns visible across enormous distances. The jet from the galaxy Messier 87, the same galaxy whose black hole was photographed by the Event Horizon Telescope, extends about 5,000 light-years into space, glowing brightly in radio waves and visible light. It's a beam of energy from a black hole, illuminating the cosmic void. Let me close with the largest beauty of all, the cosmic microwave background. This is the oldest light in the universe. It dates from about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light could finally travel freely through space. Before that moment, the universe was opaque, a dense fog of charged particles. After that moment, the fog cleared, and light started traveling. Some of that light has been traveling ever since. It still arrives at Earth today, every second, from every direction in the sky. We can't see it with our eyes. The light has been stretched by the expansion of the universe to microwave wavelengths, far below visible light. But specialized telescopes and detectors can measure it. And when they do, they produce maps of the entire sky covered in subtle patterns of slightly warmer and slightly cooler regions. These patterns are the seeds of all the structure in the universe today. Every galaxy, every star, every planet, every life form ultimately traces back to those tiny variations in the cosmic microwave background. The cosmic microwave background was discovered by accident in 1964. Two engineers at Bell Labs, Arno Penzias and Robert Wilson, were trying to use a radio antenna for telecommunications experiments. They kept finding a persistent, low-level noise that they couldn't get rid of no matter what they did. They cleaned the antenna, they repaired the equipment. They even removed pigeon droppings from the antenna's structure, on the theory that the noise might be coming from animals living in the device. Nothing worked. The noise persisted, coming from every direction in the sky, equal in intensity day and night, year-round. Eventually, in conversation with a group of theoretical physicists at Princeton, Penzias, and Wilson, realized what they were detecting. The noise wasn't from the equipment, it was from the universe itself. The faint radio signal coming from every direction in the sky was the leftover heat of the Big Bang, traveling for nearly 14 billion years before reaching their antenna. They had accidentally discovered the cosmic microwave background, the oldest light in the universe, just by trying to do telecommunications research. They later shared the Nobel Prize in Physics for the discovery. Subsequent missions, particularly the COBE satellite in the 1990s, the WMAP satellite in the 2000s, and the Planck satellite, more recently, have mapped the cosmic microwave background in extraordinary detail. The maps show the entire sky as a kind of mottled pattern with tiny variations in temperature ranging across only one part in 100,000. Yet, those tiny variations contain enormous amounts of information about the universe. Astronomers have used the patterns to determine the age of the universe to within fractions of a percent, the composition of the universe, about 5% ordinary matter, 27% dark matter, 68% dark energy, the rate of expansion, the curvature of space, and many other fundamental properties. The pattern looks abstract, almost like static. But that static is the universe's first portrait. It's the closest thing we have to a photograph of the moment when the universe became visible. From those tiny ripples, 14 billion years of cosmic evolution unfolded. Galaxies formed. Stars were born and died. Heavy elements were forged. Planets coalesced from the resulting dust. Life emerged. We are the eventual product of those tiny patterns in the early universe. The most beautiful thing about the cosmic microwave background is that it contains, in some sense, the seeds of you. When we look at maps of the cosmic microwave background, we are looking at our own deep ancestry, the pattern that gave rise to everything we know, the first light, the earliest visible structure, the universe's oldest portrait, still arriving here every second, 14 billion years after it began its journey. That is the deepest beauty I can show you tonight. Not a galaxy, not a nebula, not a planet, but the cosmic background itself. The image of the moment the universe became transparent. The starting pattern from which everything else flowed. We've walked through a lot. Auroras, Saturn's rings, pillars of creation, planetary nebulae, the Crab, galactic collisions, gravitational lensing, the Carina Nebula, beautiful galaxies, cosmic webs, eclipses and transits, and the cosmic microwave background. Each of these is real. Each of these exists tonight, somewhere out there, doing whatever it does, regardless of whether anyone is watching. But we are watching. Not all of it, of course. We can only see fragments through our telescopes. We can only photograph what happens to be in our line of sight at the right time with the right equipment. Most of the beauty in the universe will never be photographed by humans. Most of it will go unwitnessed. Most of it will exist and fade and be replaced by new beauty in a continuous, slow churn of cosmic creation. But the bits we have seen are extraordinary. The bits we have seen are enough to fill libraries with photographs, fill museums with images, fill our screensavers and our textbooks and our memories. We get to see only a fraction. The fraction is staggering. Beauty exists whether or not anyone is looking. The pillars of creation made themselves over millions of years. Saturn made its rings whether or not Earth had life. The Crab Nebula expanded from its supernova long before any human knew what a supernova was. The cosmic microwave background has been arriving here for 13.8 billion years, mostly to nobody. But we look now. We have telescopes and cameras and eyes that finally evolved to look up. We have built instruments capable of seeing things that, a few centuries ago, our ancestors couldn't have imagined existed. We have photographed the deep past and the distant future and the strangest corners of the universe. And in those photographs, we see beauty. Think about how recent this all is. The first telescope was invented around 1600. Galileo pointed his at the moon and saw mountains. He saw moons orbiting Jupiter. He saw the rings of Saturn, though his telescope wasn't good enough to resolve them as rings. He just saw two bumps on either side of the planet and thought it had ears. The discovery that other galaxies existed beyond the Milky Way wasn't made until the 1920s by Edwin Hubble. The discovery that the universe was expanding came shortly after. The Big Bang theory wasn't widely accepted until the cosmic microwave background was discovered in 1964. The first photographs of distant nebulae and galaxies in detail had to wait until the Hubble Space Telescope launched in 1990. We have lived in the era of cosmic vision for less than a single human lifetime. Generations of humans before us looked up at the stars and saw points of light with no idea what they really were. They invented stories. They created mythologies. They were full of wonder. but they were guessing. They didn't know what a galaxy was. They didn't know stars die in supernovae. They didn't know there were planets around other suns. They didn't know about black holes or neutron stars or gravitational lensing or the cosmic microwave background. The universe was a mystery they could only approach through imagination. You, lying in bed tonight, know more about the cosmos than any human in history before about 1900. You can pull up images of the pillars of creation on your phone. You can watch videos showing how galaxies collide. You can read papers about what's inside a black hole. The accumulated knowledge of the cosmos is at your fingertips in a way that would have astonished every astronomer who ever lived before our time. We are profoundly fortunate to be alive during this brief window when the universe is becoming legible. The universe doesn't care about beauty. Stars don't care if you find them pretty. Galaxies don't care if their spirals make you feel awe. Beauty isn't a property of the universe. Beauty is a property of consciousness encountering the universe. The universe makes patterns, vast and intricate, and our minds somehow are wired to recognize those patterns as beautiful. That recognition is itself a kind of cosmic beauty. The fact that consciousness exists at all in a universe that has no reason to produce it. The fact that we, made of stardust and carbon and water, can look out across millions of light years and feel something when we see a galaxy. The universe didn't have to be set up this way. It could have stayed bare and silent forever. Instead, somehow, here we are, looking up, photographing, marveling. That might be the most beautiful thing of all. Not a single object out there. The fact that we, brief and small and made of matter that was forged in dying stars, exist long enough to look up and notice. There's a phrase that astronomer Carl Sagan used to describe humanity's place in the cosmos. He said, "We are a way for the universe to know itself." The atoms in your body were forged inside stars that died billions of years ago, scattered through space when those stars exploded, eventually gathered together by gravity into our solar system, then into Earth, then into the proteins and structures that make up your body. You are, quite literally, made of the same material as the most distant galaxies. The same hydrogen, the same carbon, the same oxygen and nitrogen and iron. You are not separate from the universe. You are a part of it that has organized itself into something that can think and observe and feel. When you look up at a galaxy, the universe is looking at itself. When you marvel at a nebula, the universe is marveling at its own creation. When you feel awe at the cosmic microwave background, the universe is registering its own deep history through your consciousness. We are not visitors to the cosmos. We are the cosmos, becoming aware of itself, briefly here and there, in small pockets of consciousness scattered across a vast structure. That's not just poetic language. It's literally true at the level of physics. Every atom in your brain came from somewhere out there. The complex organic molecules required for life were forged in the cores of stars and dispersed through interstellar space. Eventually, some of them ended up here, on Earth, in conditions that allowed them to organize into living systems. Those systems, after billions of years of evolution, produced minds capable of looking back at the cosmos and asking what it means. The loop closes. The universe makes minds. The minds look at the universe. The universe witnesses itself through the minds it produced. This is not a small thing. This is, possibly, the central drama of the cosmos. The Big Bang happened with no one to record it. The first galaxies formed without anyone seeing them. Stars lived and died for billions of years before life emerged anywhere. Then somewhere, some kind of consciousness arose, and for the first time, the universe could be perceived. We don't know where it happened first. We don't know if it happened on Earth or somewhere else. But on Earth, at least, it happened, and it has been happening for hundreds of thousands of years now, and tonight, you are part of it. Lie back. Get comfortable. The universe is doing its slow, beautiful work, and tonight, you got to see some of it. Tomorrow, more. Forever, if you want. The wonders keep coming. There are more nebulae than we'll ever explore. More galaxies than we'll ever count. More cosmic events still to come, still to be photographed, still to be seen by some future observer somewhere. The universe is vast. Most of it is dark and cold. But the parts that aren't, the parts that glow and pulse and burn and dance, are some of the most beautiful things that have ever existed. We are alive at a time when we can see them. That privilege won't last forever. But for tonight, for this moment, the universe is open to us, and we get to look. Think about everything we covered. The aurora, where charged particles from our star paint our sky. Saturn's rings, soon to fade, witnessed only during this brief cosmic era. The pillars of creation, possibly already destroyed by a supernova whose light hasn't reached us. Planetary nebulae, the death shrouds of dying stars. The Crab, a 1,000-year-old supernova, still expanding through space. Galactic collisions, slow-motion cosmic dances over hundreds of millions of years. Gravitational lensing, where the geometry of space-time itself becomes a magnifying glass. The cosmic cliffs of Carina, where stars are being born inside walls of glowing gas. Beautiful galaxies, each one containing hundreds of billions of stars, each one its own city of suns. The cosmic web, the largest pattern in existence, a network of galaxies that looks strangely organic. Eclipses and transits, alignments that humans have witnessed for thousands of years. Distant exoplanets, possibly home to other forms of life. The Voyager spacecraft, drifting outward, carrying our message into the future. The first photograph of a black hole, a hole in space-time imaged by humans for the first time in history. The cosmic microwave background, the universe's first portrait, still arriving here every second. All of it is real. All of it is happening, has happened, or will happen. None of it requires our attention to exist. But because we exist, because we evolved into beings capable of looking and understanding, all of it can be witnessed. We are the first generation in human history that can see the universe in this kind of detail. Every previous generation looked up and saw stars, but they didn't know what stars were. They didn't know about galaxies. They didn't know about black holes, or nebulae, or the cosmic background. We do. We are the witnesses our ancestors couldn't be. What a strange privilege. To be alive, briefly, on a small planet around an ordinary star, in a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies, and to be capable of understanding our place in all of it. The size of the cosmos doesn't diminish us. If anything, it's the opposite. The fact that we can comprehend something so vast, that our minds can hold maps of structures spanning billions of light years, suggests something remarkable about consciousness itself. Whatever we are made in such a way that we can look at the universe and grasp it. That's not a small thing. Good night. Sleep well. Out there, the cosmic light keeps arriving. The pillars keep collapsing. The galaxies keep dancing. The cosmic web keeps glowing. And somewhere, right now, a star is being born in a nebula too beautiful for words. You don't have to know it's there for it to exist, but it's nice to know, isn't it? The universe is making things of beauty all the time, everywhere we look. That's the gift. That's the wonder. That's the reason to keep looking up. There's an old Persian poem that says, "Somewhere out there, the morning is breaking on a world we'll never see." That's true in our universe, in a literal sense. Right now, on countless worlds across the galaxy, suns are rising. Storms are forming. Auroras are burning. Comets are passing by. Continents are shifting. Mountains are growing. Each of those events is happening for nobody, just doing what cosmic events do. But they're happening. The universe is busy. The cosmos is full of slow motion. We catch glimpses here and there when our telescopes happen to be pointed in the right direction at the right moment. We make photographs. We feel awe, and then we go back to our lives, knowing the universe keeps moving without us. The light coming to your eyes from the most distant galaxies left them billions of years ago. Some of those galaxies might no longer exist by now, but the light is still arriving, still carrying their image to you, across all that time and distance. The galaxies you see in deep field photographs are time machines. You're seeing what they looked like before Earth existed, before our solar system formed, sometimes before our galaxy itself fully assembled. Looking at them is, in a sense, looking at the deep past of the cosmos. And the light you see right now, from your bedside lamp or from the screen showing you these images, is racing outward into space. Some of it has already passed the moon. Some of it has passed Mars. Some of it will, in millions of years, pass through other star systems. If any alien astronomer is looking at our sun from far enough away in the right direction, they'll eventually see, faintly, the light we're producing tonight. The cosmos is full of crisscrossing beams of light, each one carrying a tiny message from somewhere. We're broadcasting too. The universe is listening, even if no one is replying yet. Sleep well, traveler. The light is still coming. The universe is still being beautiful, all by itself, whether or not anyone is watching. And tonight, briefly, before you fall asleep, you got to be one of the watchers. The universe noticed itself through you, just for a little while. That's enough. That's plenty. That's more than most matter in the cosmos ever gets to do. Good night. Rest well. The wonders will still be there tomorrow.